And right away, I want to clarify that it's NHATS, not NHATS. And Lindley would be happy to hear that, I'm sure. And you see that we're talking here about human space flight to near-Earth objects. So these trajectories I'm going to be discussing are round trips, essentially. The task is to assess all known NEOs, identifying those having at least one round-trip trajectory compliant with all the NHATS constraints. So the ones we're really going to touch on and emphasize are that we need to depart Earth between the 1st of January 2015 and then the 1st of January 2041 is sort of the end of our assessment window. And there's all kinds of trajectory constraints, and I'll refer you to the website down at the footnote there for the details. But we're also going to look at the constraint on 12 kilometers per second for the total delta V, and that's starting in low Earth orbit. An impulse sends you out toward the NEO you're interested in visiting. You stop, you stay there for at least 8 days, and then another impulse sends you back toward the Earth. And then if necessary, you even have an impulse to control your entry speed to less than 12 kilometers per second, so you don't have to design some kind of crazy thermal protection system. And then finally, a really important constraint we'll be discussing is the delta T tote. You need to do it in less than 450 days. Now, these are pretty wide open constraints given where we are right now in human spaceflight. I mean, most human missions to the International Space Station are 6 months, and here we are well over a year in this constraint. But suffice to say that many of these constraints are motivated by an envelope that puts you with less time and less delta V than it would take to go to Mars in any mission mode that's realistic. So if you're thinking about the context of this, it's designed to show how many of these NEOs are more accessible than a Mars mission would be as measured by these metrics. And look today, and we're up there at like 2007, almost to 2,700. It's like 2670, I think, is the count of NEOs that have at least n equals 1. And some of them, as we'll see, are up there in the millions in the 26-year period. So we're talking big data here when you're trying to analyze how accessible is an NEO. And this, of course, is a very subjective measurement, and there's a lot of really good material in that footnoted webpage on the subjectivity of accessibility. One of the really important parameters that isn't advertised much is this delta TDA that's set at 8 days right now. And what it does is it says, okay, we're going to increment the departure time and arrival time at the NEO, and then the departure time from the NEO and the arrival time back at Earth by these 8-day increments. And what that does is it potentially, at least, if n is greater than 0, generates multiple distinct NHATS-compliant Earth returns nested in each single Earth departure trajectory. And I've tried to give you a little bit of a taste of what that means with this bat chart here. So you've got the Earth at the bottom, the NEO at the top that you're going to, and then time flows rightward. And we have our little increment here, delta TDA, and then each departure is color-coded. So I'm talking about this initial departure here is associated with some kind of dwell time at the NEO, and then you have a whole bunch of red return trajectories that spawn off of that. And then, you know, you increment the departure time by delta TDA, and now you have the orange family arising from this one outbound mission. You have a whole bunch of orange return missions coming back to Earth. And as the note decries at the end here, the multiplicity of missions that you see here isn't all the degrees of freedom that NHATS actually assesses, the NAT software, because the slope of all these lines is parallel outbound, parallel return. So that means the transit times are all the same. And that's not what's actually being done. It's much more complicated than that and would have involved with even more of a blizzard of crossing lines to actually depict it. And you can imagine that at each outbound point arrival at the NEO is a little dwell time, and then you get a return that need not be at that same slope, and it can actually pivot. It gives rise to a whole bunch of returns that have that NEO departure date in common. So you just have this blizzard of crisscrossing lines if you were trying to really plot all the NATS compatible missions to a single destination on a bat chart. So it's a bat chart like no other you've seen. Not getting in advance here. Okay, time delay. Okay, and NATS in a nutshell continued. I mean, here we do all these assessments. Here's the output that we get basically for each NATS compatible NEO. For n greater than 0, to generate digital output for the round trip with the minimal time of flight and the minimal delta V. And so you get these two digital sets of output that give you the timeline of the mission and the delta V of each impulse and various other targeting information. And then what I call an icicle plot, I don't know if that's a common terminology, but you'll see why I call these icicle plots, which is, whoops, don't touch anything? Don't worry. Okay. Can I use the pointer? Yeah. Okay. So then you get this icicle plot, which is delta V tote, which is the delta T tote versus the departure date on the horizontal axis, and then color-coded with delta V tote for all these end missions. And the coding I've done shows that this is sort of like a contour map, and so you can't see the lower layers, and well, I'll explain more. So that's what you get on the output. And so what I've done is created what I call the NHATSchecker utility, which is the only known independently implemented NATS knockoff. And I've checked with a few people like Frank Barbie, who was in on the original development, and the current developers and operators. And so this is the first independent check. And as you can imagine, what one person thought were clear implementation requirements, I've gone and found many ways of reinterpreting those. And so it's been a very interesting finding out what the sensitivities are. It's just really an exercise in sensitivity analysis for what NATS does. So we assess NATS constraints against only one specified NEO, because I don't have a gang of computers that the Center for Near-Earth Object Studies has. And then provide a user interface, and this is the fun part, where you can go and tweak these NATS constraints from their default values, and then supplement the NATS digital output and icicle plots, and I'll hopefully have time to show you that. So we're going to explore the dependency with these preliminary results of N on the minimal outbound and return time of flight. It turns out I was thinking that delta T DA was 8 days. That meant the progression of times of flight outbound, let's say, just for simplicity's sake, started at 8 days, then went to 16, and so on. Well, it turns out the real NATS software starts at 1 day and then goes to 9 days and then to 17 days. And you think, oh, well, that doesn't really matter. I mean, I might not want to fly a one-day mission out to an NEO that might require warp drive, but we'll see that not even with NEOs that couldn't possibly have a one-day time of flight, this really matters. Then also going to assess, look at the sensitivity of the Apophis icicle plot to the first assessed departure date, because there again, we had a disconnect. I thought, oh, we're starting on January 1st, 2015. That's my first date to assess. Well, it turns out the real NATS software starts 4 days later, halfway into the delta T increment. So there's some interesting variations there that result. And then finally, we'll look at the effects of slipping Earth departure dates to eliminate those in the past, because right now we're approaching 10% of the missions are in the past and are therefore of very little interest. They started in 2015, and they have great historic precedence, I guess, but we want to think in terms of marching that window of departure dates forward so that, well, one ops concept I'm advocating currently, but I'd love to hear others, is that every year we go and advance the opening of the departure dates to January of that year. So this year, we presumably would have done it January 1st, 2019, and then extended for another 26 years. But the thing to remember is every time you do that, you have to run the NATS software against the entire catalog of known NEOs. And some of them are going to be running lickety-split because they have n equals 0. But others, as I say, are up in the millions. So we'll look at one of those cases. That happens to be 2000 SG344. So let me press on in here to show you some results. So here's the time of flight. Minimum time of flight really affects N. And I'm talking on the order of 10% N variations. And so what we've done is, you know, the delta T tote could be as little as 1 + 8 + 1 in the NAT software. You could get a 10-day mission, but I haven't seen any good examples. I'd love to hear of any, if anyone's happened to cross the big data needle in the haystack. And the N is affected regardless of the NEO's minimum orbit intersection distance, the MOID, the MOID. And that's the part that really had me doing the double take. So I was first looking at really small MOIDs like Apophis, where it's in a fraction of an AU. And you can see like little 1 to 2% variations in N. And you can see in the second column, NATS uses a minimum time of flight of 1. Well, I could change NHATSchecker to do that too, and you get pretty good agreement, you know, to 3 figures, almost 4 figures. And then when you go to 8, where I first started out for a minimum time of flight, I'm down there lower by about almost 2%. So that sort of gives you an idea of what the subjective noise level is when you look at a NATS output. So there's a bunch of missions. 2000 SG344 has a really small MOID, and it's, I think if you don't care how big your destination is, this is the largest N in the catalog right now. So this is the largest or most accessible, and I use the term subjectively, NEO that has, you know, size on the order of 100 meters or so. And you can see 3,300,000 if I do it with NHATSchecker. So I was thinking at first, oh, I'm always going to wind up with fewer missions, but in this case, no, I didn't. I wound up with more missions, which just again shows different implementations are going to give you an idea of what kind of variations to expect maybe in the real world. And then going to 8, I wound up with less again. Down here, I went to this 1996 XB27, which is reasonably accessible, but because it's an AMOR, it's always outside the Earth's orbit, and therefore the MOID is 1/10 of an AU. And you can see it still has good variations. It's almost bimodal, depending on what your minimum time of flight is, bimodal N. And variations on the order of 10%, just less than 10%. So there's a lot of variation in there, just depending on how you want to implement this kind of function. For possible future modification to NATS, we may want to consider keeping N, you know, a good bit greater than 1 day. I'm recommending 8 days, simply because the crew just doesn't have time to get to a you know, NEO rendezvous in 1 day after they depart Earth, nor do they have time to configure for entry 1 day after departing an NEO. So It just doesn't make sense if indeed there are any of those missions, and I haven't run across one. So 8 days, that's the recommendation. This is what a NHATS icicle plot looks like. And I was visiting this with Paul Chodas last night. Apparently there's been an enhancement so that this particular icicle plot is for Apophis. And it is on the year, on the order of years old, because we don't have any new observations of Apophis until I think a year or two from now. And so this is older software than we have currently doing these plots. And the plots look more like the ones I'll show from NHATSchecker. If you look at like XB27s was the one that cued me off on it, because it had observations that were processed this month. But this is what it looks like. And, you've got this color-coded delta V. So blue is good, red not so good, yellow is intermediate. And then you have the round trip time in days. So lower is better than higher if all other things are equal. And then across the horizontal, we have the departure date spanning the 2015 to 2041 time frame. And the thing to note about Apophis is among more accessible NEOs, these are very sharp icicles. That's the best way I can describe it. Because I think, mainly because Apophis has appreciable inclination on the ecliptic. So if you're just doing these bang-bang kind of transfers where you depart and arrive, you're going to be better off if you're really near the node when you do the transfer, if everything works out. So you have real time sensitivity here. And notice that this center icicle has 2 minima in time of flight, and the left one is more is less, it's a lower minimum of time of flight than the right one. And here's what I came up with my first NHATSchecker run. I've got the same setup where blue is good, red ain't so good, but notice my minimum here where I put a little circle marker to show the software actually detected that this is the minimum time of flight. It's the later of the 2 icicles. And so that set me on to consulting with Paul and his folks about what exactly are you implementing and can I get a better match? And when I found out about, I'm starting January 1st for my first assessment. I'm exactly out of phase with you guys by 4 days. So if I start my first assessment on the 5th of January, what do I come up with then? And just keep that in mind as we switch. We icicle from that. And now you see I'm in sync with the original icicle plot from NHATS. The early minimum matches up. So that mystery was solved. And then here's another what if that I mentioned that we did with 2000 SG344, which the NHATS plot for it shows you this is a really accessible NEO. Look at all the blue in the middle here. Not much in the wings. There's just this huge set of missions that are clustered around 2029, circa that year. Here's what I got from NHATSchecker, and yeah, it matched up real well, probably because the icicles are not nearly as sharp. They're much more easygoing. There's broad sheets of ice. It's more like a glacier than an icicle. And because of that, I was getting really good matches on minimum time of flight date, minimum delta V here in the blue. There's even a minimum dwell time, I think, up in here somewhere. So that's the maximum stay time at the NEO, which I was also computing by that time. So what happens if we slip the Earth departure window so that it opens when this one closes, when the standard NHATS processing closes? And here's what you get. Nothing until almost the end of the 26-year period. In fact, there's a 3-year period where the 26-year window fails to produce any compliant missions. So you wind up with N equals 0, and 2000 SG344 goes from one of the most accessible missions to not accessible at all. It won't even be on the list for 3 years. So something to bear in mind if we elect to go ahead and start slipping that launch date over periods of decades. And this is all because 2000 SG344 has a synodic period that you can measure in like decades, probably 25, 30 years. Then it comes close to the Earth, gets perturbed, and that changes slightly. So it's really a subjective number when you say, oh, it's got N equal 3 million. It's perishable. And based on a preliminary white paper that I sent off, I got some feedback from someone at headquarters that, well, why don't you plot the dwell time at the NEO? Let that drive the color, because that's what really is the payoff, right? You're sending humans into interplanetary space on a mission that might last a year or more. How long do I get to stay at the destination and do science and stuff? And so that led to another short programming effort. And this is 2000 SG344 with now dwell time at the destination in days, driving the color. So blue again is good. And you can see that we get into some nice long dwell times up here, but unfortunately they have high delta V's if you actually run those missions down. And another possible color driving parameter for icicle plots would be, what's my point of no return? How long can I stay on my outbound trajectory and have enough propellant, the 12 kilometers per second, let's say, so that left over, so that I can then turn around and come back to the Earth in less than 450 days or whatever that parameter is. So I want to extend all that. These nested trajectories are fascinating to play with, and it's definitely big data games that I can stand some education on. If anyone wants to correspond with me, my email's down here, and I'd be interested in any ideas or feedback. That's all I have. And I'll be glad to take questions.
Another possible use for this beyond human exploration is asteroid mining, to determine asteroid mining targets, right?
Right.
And those will have some things that they want to optimize the same and some things they don't care about so much.
Right.
Do you think it would be difficult to change these implementations to say, oh, either we don't care how long we stay, we can make it a
huge number
long, or yeah, okay, 1 day is fine. If you imagine some future where something's just doing something fast and taking off.
Definitely.
Can you kind of repeat the question?
Yeah. Oh, yeah. The question was, could you change these parameters so that it might support other endeavors than human spaceflight, like asteroid mining, and therefore you're talking about a one-way trajectory there, and you may not care what your time of flight is. Maybe you're thinking about something else I've considered, is going on to another destination rather than Earth. And so you have a two-leg trajectory still, but it's not a round trip. And then that opens up all kinds of interesting possibilities, like what's my optimal way station on an Earth-Mars trajectory? Assuming we get electric propulsion a la ARM, and we can start jockeying main-belt asteroids or near-Earth objects around to these optimal places, it may not take much delta V to get a really strategic orbit. And so what is that orbit, and what's nearby? So yeah, I follow exactly what you're saying. Yep. Yes, Paul Travis.
Yeah, Paul Travis, JPL. NHATS has been operating for a number of years now, and I think it's wisely pointed out that other things that can be done with this tool. And so I think it's a good thing for the SBAG to discuss what direction we want to take NHATS in, and NHATS 2.0. It's now in-house at CNEOS at JPL, and so we have some abilities to move in different directions. But what is most useful, and is the question to the community, for the next level, next version of
And Paul is asking a question that I would love to see turn into a finding, which is how best can the NATS software at CNEOS evolve to support not only human exploration, but the many other endeavors that hopefully SBAG will come to embrace. And of course, that sort of gets into the whole in situ resource utilization bailiwick as well. So, yeah, I hope the answer is we can write a finding and maybe an ongoing one that requires modification. Any other questions? Okay.
How about adding low thrust trajectories to NATS?
How about adding low thrust trajectories to NATS? And I'll tell you, my version of NATS is not the fastest, and it's probably because I don't have a really well optimized solution generation for Lambert trajectories. But even the NATS software that's been optimized that runs every day can take a while to crunch through something like 2000 SG344 generating 3 million solutions. And these are semi-analytic solutions, right? They are Lambert trajectories, so you have to iterate, but it's on an analytic equation, okay? With low thrust trajectories, you're talking about at least an order of magnitude more for each mission to generate. And so I think the answer is, that would be nice, but it's a huge computational burden. Yes, Paul.
And that's the question, basically, that could be put into this finding. I mean, that's an example of an extension that, and we've looked at that a little bit at our CNEOS and solar system dynamic software. But it's a formidable computational issue, so it needs to be considered carefully.
And so Paul Chodas is answering that the finding might want to include what we're suggesting here, what's suggested by this question, maybe doing some low thrust